At the end of the lesson, you are expected to identify the effects of multiple dimensions on deep learning algorithm, visualize the status of local minimum vis-a-vis the condition of second derivatives, and appreciate the significance of multiple dimensions in deep learning algorithm. Let me begin by saying that the second derivative is used to identify if a critical point is a local maximum, a local minimum, or a saddle point. So I believe you have already understood what a local minimum, a local maximum, and a saddle point are. So now let's remember that a critical point, which is the first derivative of x, is equal to 0. Okay? So given this value of the first derivative, it means that our second derivative of the function x is greater than 0. So at this point, the best question to ask is, given these values, what is the effect to the direction, or what's the effect of the direction of the movement? So the answer is this. So please listen very carefully because this is very important. Okay, so the first derivative increases as we move to the right. So when we move to the right, it increases. It's like that. So please take note of the direction. Again, let me repeat this because it's very important. When we move to the right, the first derivative increases. And obviously, if we move to the left, then the value of the first derivative decreases. Okay? So visually, when we move to the right, the slope is pointing uphill to the right, and when we move to the left, the slope is pointing uphill to the left. Does this one make sense? So, based on these two scenarios, what interpretations can we make with respect to x? So this is a very good question, so we have to take note here of two situations so that we would be able to understand the relationship between the first derivative and the second derivative. Okay? So the first situation is this. The first derivative is equal to 0 and the second derivative is greater than 0. So if this is the case, then x here is considered a local minima. Let me write this. So this is x is considered a local minima or minimum, okay? Depending on how many points do you have. So our second situation is that the first derivative is equal to 0 and the second derivative is less than 0. As you could see, this is greater than, this is less than. So if the case is like this, then x is concluded to be the local maximum. Let me write this one again. Local maximum. Okay, maximum. So if we're going to make a drawing, just for you to be able to see this one very properly, for number 1, the case would be like this. And x is here. And here in our number 2, the case would be here, and our x is there. It's the local maximum, right? So these two scenarios are known as the second derivative test. Again, these two scenarios are what we call the second derivative test. So now, let's consider the situation when the second derivative is equal to 0. What would be the effect? So if the situation is like this, then x may be a saddle point. Let me write here, it can be a saddle point, or it could be a part of a flat region. It could be a part of a flat region. Okay, so flat region, saddle point. So if we are going to make a drawing, it could be like this. Okay, and our x can be found in this flat region, right? Does this make sense? Does it register in your mind now? So before we continue, please hit that subscribe button to enjoy more of our deep learning, machine learning, and natural language processing lessons, and all are for free. So this time, let's go to a matrix with multiple dimensions just to make everything very interesting, because what we have here is a matrix with only one dimension. Let's now go to a matrix with multiple dimensions. What are we going to do here to better understand the critical points? So don't forget these critical points. So for us to be able to make a generalization of the second derivative test to multiple dimensions, we are going to use the Eigen Decomposition of the Hessian matrix. So at this point, I really expect you to have some knowledge about Eigen Decomposition. If you haven't yet have some knowledge about this concept, I suggest you study or make a review about what this one is and how to get this one, because this is really very important, especially when we talk about the principal component, the SVD. Okay, so this time we will again use the concept of Eigen Decomposition to better understand the relationships between the different points in our Hessian matrix. So at this point, I really expect you, okay, so just like the case of a single dimension, in multidimensional, where we have the gradient of x of the function x is equal to 0. So we can also examine the eigenvalues of the Hessian to identify if the critical point is a local maximum, a local minimum, or a saddle point, just like in the case where we only have univariate cases. So to better understand this, we have to take into consideration some situations that we have to always remember. Okay, so let's first have the first situation. So here, the Hessian is a positive definite. Maybe you would like to ask me, what is a positive definite? A positive definite Hessian means that all its eigenvalues are positive. Okay, so in this case, the critical point is a local minimum. Okay, this is the critical point is a local minimum. Local minimum. Okay. So if you're going to draw that, the shape would be like this. Okay, but then of course it's going to be a 2D or 3D, right? It's not going to be like this. Which one? Okay, not like this one, right? But then just for the sake of simplicity, of course, we're going to have just something like this. We are just considering here points, okay? But then again, this is in a 3D or 2D format, okay? So the point could be here, right? So our second point is when the Hessian is negative definite. So it means that all its eigenvalues are negative. So this is just actually the opposite of the first one. So what would happen if the case is like this? So if this is our case, the critical point is a local maximum. Let me write that. Okay, so now in this case, we have the local maximum. Okay, and of course, because it's local minimum or maximum, then we have to expect that point x is on the top. So if this is our shape, then the local maximum is here. But then again, as what I have told you, this is just a representation because this is a univariate, but what we're looking here is the situation of the point, right? So what if we can see both situations in our Hessian? So it means that we have at least one positive eigenvalue and at least we have one negative eigenvalue. So in this case, we can have x as a local maximum on one cross-section, and on another cross-section, we can see a local minimum. So if we're going to make a shape, then what would be the visual? But again, I would like to point out that we are pointing out here the points because if we're going to draw, it's going to be a 3D or a 2D format, right? But for the sake of us pointing out or identifying the point, then we're going to just have this very simple drawing. Okay, so again, we can have x as a local maximum on one cross-section, and on another cross-section, it is a local minimum. Okay, so it could be like that. Okay, so as you could see here, points or 2 points can be found on both sides. Okay, so we can have the sides on the negative one and we can have a point on the positive one. So here we can find the local minimum, and on this side we can find the local maximum. So this is the case if we have at least one positive eigenvalue and we have at least one negative eigenvalue. Okay, the next situation is all of the non-zero eigenvalues have the same sign. So it can be positive, it can be negative. Also, we have at least one zero eigenvalue. So here, the multidimensional second derivative test can be inconclusive. So this is the same case in the univariate version. Maybe you would like to ask, so what is the reason behind this kind of situation? The reason is that the univariate second derivative test is inconclusive test in the cross-section corresponding to the zero eigenvalue. What is this for? Why do we have to study this? Eigenvalues and eigenvectors are very important in linear differential equations. It finds applications in determining a rate of change or deciding whether or not to maintain relationships between two variables. After all being said and done, let's try this. What are the different scenarios that affect the condition of the critical point? How does the Hessian affect the deep learning algorithm? Do you want to know more about this course? Just click the video on your right screen. I have a lot in store for you. I have courses in deep learning, mastering machine learning algorithm, and natural language processing. You can learn and upskill yourself all for free.